Hello, I'm Dr. Nicholas West, spectroscopy specialist at Andor for Europe, Middle East, Africa, and India. Today we're having a more advanced video on the iStar sCMOS external triggering, considering things like impedance and ringing, grounding, and jitter. So today I will show advanced trigger setup circuits, but I'm not an electrical engineer. So I will explain these circuits through analogies, and I assume that engineers that want a more rigorous description will be able to make their own circuit simulations and calculations. So the first topic that we'll be covering today is signal ringing and reflections that can occur when the system is not impedance matched, and what does that actually mean in general. So again, these slides are going to be highly oversimplified, taking out the mathematics of it, but to just show some graphs and explain through analogies. So the first setup that I will be discussing is using a digital delay generator, a BNC to SMA cable, and an iStar. So we'll connect and trigger the iStar through the BNC to the SMA there to the external trigger of the iStar. So in this simplified circuit, don't worry if you don't know much about circuits. I will explain this through the analogy on the right to a water pump circuit. So first of all, the first component of each of these is the pump of the system. The thing that's creating the pulse of, in the electrical circuit, it's the voltage pulse, the TTL pulse that's traveling through the circuit. So this is the digital delay generator here, and sometimes this has a resistance to the pulse with built into the delay generator, and sometimes you pick it within the settings, or you can externally add a resistor in series when required. So you would need to read the manual for each delay generator to know what it needs. So in this case, the analogy is showing that for our water analogy here, we have a pump that takes water from a low pressure region, the analogy to voltage, to a high pressure. It may have some resistance to the flow and built into the pump itself, but it brings it to a high pressure region above, where it then creates this wave or pulse that travels through the rest of the system. The next component here is the cabling that you can see is just the lines connecting the two resistors. And the properties that you need to care about for these cables are the impedance, so I'll define that in a moment, and the length of the cable. In this particular simulation that we'll be showing, it's a 2-meter long cable that requires about 10 nanoseconds for the voltage pulses, the TTL pulses, to travel along this cable from the delay generator to the camera. And so in our analogy, that's represented by these big tubes that connect the different resistance loads and pumps of the system. And so this is what the wave travels along, or what that voltage pulse travels along to get from one side to the other. And so now I want to define what impedance and resistance are. So impedance is the frequency dependent opposition of the pressure or flow of charge. So in our circuit, it's the it resists the change of the voltage. So our voltage pulse is almost instantaneous jump in voltage, and so it's the ability to resist that if there's a difference in how that can travel through the individual components. So that would be, in this case, the resistance of a wave traveling through the water pump circuit that can slosh around back and forth if the different resistances to that flow are not well matched in the system. And so this other component over here is the resistive load, what's doing the work in the system that dissipates that wave that's been sent through the system. And so in this case, we set this to 50 ohms as well in the iStar. And so this tight place in the water circuit is where the wave could meet resistance to flowing. And then another component here is the source of zero pressure or zero voltage, zero anything. So here, these are grounding symbols. So generally the power cable that goes into this power connector has a grounding pin. Sorry, these are a few examples of locations where I've used power cables, but sorry if I've not represented your own personal country or region. But essentially, if you either use the power cable that has the pin to there, or there's a grounding pin that you can alternatively attach to the ground as well. And so what that represents is a large reservoir that has so much water that essentially it keeps this side of the system at zero pressure. And so when I say impedance matching, what we really want to be able to do is make sure that these resistive and impedance loads in this circuit are well matched to each other, so that this wave of this electrical pulse or this wave traveling through the circuit doesn't meet a difference in resistance that would make it slosh around and ring back and forth in the system. And so then if we were probing different parts of this circuit, we can see how this can be affected by the system. So this is a relatively simple system, so it will not be affected quite as much. So the first thing we would probe is directly at the source, right before the resistive load. You can see that it creates the approximately 5-volt TTL pulse. That's around 10 nanoseconds wide. We then have the source out that goes to a lower voltage that we'll talk about in a moment. And then if you were to probe the load itself, it has to wait for the delay of the signal to reach there, so it starts a little bit later and is the same height. So in this case, you can explain the height due to the two resistances in series that have the voltage when it's traveling through them. And in this case, one thing to note is that the minimum pulse width is the same as a 1-trip delay, so you can't have a pulse that's narrower in time than the time it takes for the pulse to travel through the circuit. And in this case, this system is well impedance matched if these are new components with no wear on them. So in this case, this wave that travels through, it stopped in the first reflection, so it does have a little bit slower of a rise time, but you don't see this signal jumping up and down. And so in this case, although the trigger level is programmable between 0.25 and 3.3 volts for the iStar, you would want to make sure that you're triggering below this 2.5 volts so that it can actually find that rising edge there. And so in order to set this up in your system, there's a certain setting in the menu. So if you go up to the top left in Solus to the hardware menu and go down to I/O control, this window will pop up, and this is where you can change between 50 ohms or high impedance, in this case 10 kilo ohm options. Additionally, you can set the threshold right there. And so now the second case is when you're not doing impedance matching. So in this case, you have 50 ohms, but if you change the impedance of the iStar to 10 kilo ohms, then this changed the effects of the circuit. So if you first start looking at the source again from that same location right by the pump, you can see that it requires a longer pulse because it requires a round trip of that pulse or that wave sloshing around. So the minimum time is for a round trip, so about 20 nanoseconds. And so then you can see that because there is the ringing back and forth in this circuit, you see this jump in voltage coming through. And finally, at the load, since it's a high impedance, you see the voltage is actually higher, but it's a little bit not as steep as it could be. So then, just to do a bit of comparison of why you would choose one or the other, if you can configure you can still get it matching when you're using high impedance, but you need to make sure that all of the impedances are matching between your delay generator, your oscilloscope, and your iStar to get the best effect. So some instruments can only do one or the other. So you need to look at the manuals of the equipment that you're using and consider that. And so now I can talk a little bit about why you would choose one type of impedance or another. So if you look at the current values from the previous examples, I had an electrical engineer do some simulations for me. You can see that you can pick your resistive load, either 50 ohms or 10 kilo ohms on your iStar. The 50 ohm load has a much higher average current, and so higher power usage overall, but has a slightly lower peak current. So this means that if you make especially if you make a wider, longer pulse, it will use more power, and some systems are simply not built to handle these high power 50 ohm loads. So you need to check with your manual whether or not it's able to set that up. Whereas overall, you're using less power on average for the mismatched high impedance system, but the peak signal goes high. So you want to watch out to make sure that the peak voltage and current don't exceed that of the rating of the equipment that you're using. And so overall, you want for the iStar, it is designed to be used. I have the numbers on the next slide, I think. Slightly, you want to basically keep it above 0 up until 5 volts and then stay within that range of voltage, always positive. So in the first example that we were looking at, the 50 ohm impedance, again, it had nice sharp rising edges, but it had more power usage. So make sure their instruments are rated for this. And in our kind of example of mismatching the impedance between the systems, it created more ringing and peak signal intensity that can exceed the ratings of the components of your instrument. So you want to make sure that you're not damaging your instruments by mismatching the impedances. And so if you want to test this at home, I would highly recommend to make sure you're substantially lower than 5 volts in your pulses, so that even if you do see ringing, that ringing would still be below the 5 volt maximum value. But then overall, you can play with maybe the impedance. You can set that to 10 kilo ohms in the iStar and 1 mega ohm in the oscilloscope, and you are probably going to need to zoom in on the timescale to about 4 microseconds per division to see some of this ringing. So in this example, we're going to add an oscilloscope. So this was our original circuit and our original analogy, but when you add on the oscilloscope here, you can see that this TTL pulse is split between going there to the camera and traveling along this pathway to the oscilloscope. So in that case, the analogy is you're adding another resistive load that splits that wave in between these two channels. And so when this happens, you have nice long cable lengths that you have to travel along. So in this case, we made a longer width of the original pulse from the source. But then the next two signals look at are in green. We have the iStar signal that if you probed right here in the circuit, and the oscilloscope signal if you probed right here in orange in the circuit. So you can see that the iStar signal in green has this ringing behavior there, as well as when it's returning again down in voltage, whereas the oscilloscope has a slightly different yet quite similar ringing profile as the iStar. And so again, you're now this is slightly exceeding that 5 volt maximum value if you're not careful. And so it can go, you can input anywhere from negative 0.3 to plus 5 volts, but essentially just think you always want to use positive pulses below 5 volts in your iStar. And so now when you're considering triggering, this can make some complications. So first of all, it looks okay if you trigger right here. If you trigger the iStar, if you're looking at the green curve, you can see that it hits one rising edge, and that's where it will trigger each time. However, if you look at the rising edges for the oscilloscope, you can see that there are 3 rising edges, so maybe your oscilloscope will sometimes trigger off of this edge, sometime this edge, sometime that edge. So it may not accurately represent as well what's happening in your system. So this is one complication to try to consider when you're attaching multiple working components into the same system. And so again, here's a screen trace of an oscilloscope that you want to avoid, because if this pulse height is 5 volts, you can see this goes substantially higher than the 5 volts while it's ringing. So do make sure that this total signal is lower if you do have to mismatch the impedance. And this is likely to vary in real life because your cables could be longer, and if your cables are worn out, they might have slightly different impedances than when they were originally manufactured. Okay, so for another example, again, make sure you're using less than 5 volt pulses. In this case, we're going to do impedance matching. So have a 50 ohm impedance selected for the iStar. Same for the oscilloscope, another 50 ohms, and similar times per division and 4 microseconds per division. And so in this case, we have the same circuit here, except that the resistive loads are now both 50 ohms. And so your original signal again is at 5 volts, but since you have this type of resistive load, your voltage drop across them causes this drop in voltage here. So overall, you're left with a 2 volt tall pulse that you have to trigger off of. So you're going to need to make sure that when you're triggering your iStar, that the trigger threshold is lower than 2 volts to be able to trigger it properly. So here's essentially the same slide as previously. I believe that the parameters are quite similar, but I need to ask another electrical engineer to finish off the other currents that I've not got on the second part of this. But overall, the 50 ohm impedance matching allows for sharper rising edges, but has more power usage and has lower trigger thresholds that it needs, whereas the impedance mismatching of the high impedance caused ringing that could also lead to a situation that you want to avoid to damage your components. So a few other troubleshooting steps. So first of all, if no oscilloscope is available, then you want to, you can still achieve the same effects of finding the signal that you need to measure, but you're going to have to start with a really long exposure and a really wide gate, and then slowly step in from each side until you see the signal go away, and then adjust back out until you're sure that you're only taking signal where you have actual light from your sample. So another troubleshooting step is that if your oscilloscope, maybe it cannot work at 50 ohm impedance, and if it's causing ringing, sometimes it could help to just remove your oscilloscope. Then again, I mentioned earlier that sometimes you can have old wires, so the impedance are not sometimes currently what they were originally when they were manufactured. So sometimes if you just change out wires, this can solve some of these problems. And sometimes just changing the length of the wire can affect the properties of the circuit as well. So the next type of phenomenon that I want to talk about, and the next thing to consider, is the grounding of instruments. So here I want to say that any metal components of instruments, whether it's laser tables, optomechanical mounts, or other things, they can act as radio frequency antennae, or they can get induced currents from inadequately shielded electronics. So one common example of this in any laboratory is just the power line noise from the AC power from the walls. So that would be around 50 hertz in the EU and around 60 hertz in the US. Or any of these can build up static electricity. So overall, one way that people try to reduce some of these noises in their metal components in their lab is to just wire all of their instruments to a ground pin of an electrical outlet. think I've shown in previous slides. Another thing you can try to do is to build Faraday cages around your sensitive equipments so that you can shield the electrical components, but this is not always practical to do. So the last effect to consider in your measurements for today is jitter. So first, what is jitter? So it's the time displacement of pulses. When you have multiple different pulses, do they jump back and forth with respect to the other things that are pulsing? And so there's always a finite small amount of this in any electrical circuit that you make. So you can see this if you turn on persistence mode of an oscilloscope. And so what the persistence mode is on an oscilloscope, I think this is a common feature in oscilloscopes, is to overlay multiple traces on the same oscilloscope screen. So here's an example of showing jitter in the fire sensor exposure during a direct gating simulation, or actually demonstration. So we actually measured this on an oscilloscope. And so what you have here is an external trigger pulse. I'm only going to go over some of the ones that are important for this discussion here. So here we have an external trigger coming into the iStar. There's the fire pulse here, and so you can see that when you have multiple of these lines overlaid over each other, you can see that if you're triggering off of the external trigger, there's more jitter, there's more pulse-to-pulse variation in when this rising edge happens in the fire pulse with respect to anything else in the circuit, whereas the gate pulse has very minimal jitter. It's basically a solid line all the way through, and so essentially what you're going to want to do is, this is telling you that your sensor is not always ready to pulse at exactly the same time, or is not always ready to accept photons at exactly the same time. So instead, you would want to move this gating to happen after this variable amount of jitter to when this sensor level is high. Yeah, again, it's normally recommended to gate after this jitter part here. So now I want to talk about a few things that you can do to avoid the effects of jitter. So the way to lower the amount of jitter from an external trigger, so you may recognize this picture from a previous video that we've done when you have an external trigger coming into the iStar camera, is to set the trigger level at the steepest part of the rising edge, so right here, because otherwise there's a bit of noise on the that more greatly affects the slowly rising part of a trigger, and so there would be more variability of when that trigger actually occurs. So here, that steepest part is typically between 1/3 to 1/2 of the peak amplitude. And so now I want to answer the question of what amount of jitter can you typically expect from the iStar digital delay generator? So in general, the properties of the iStar digital delay generator are actually quite similar to pretty standard digital delay generators on the market. So in that sense, there is a less than 35 picosecond typical RMS value of the jitter. So this is a function of the generated time delay. So what that means is if you have a longer time delay, there will be higher amounts of jitter in between pulses if you have a longer delay between pulses. And also the peak-to-peak jitter is roughly 5 times the RMS value. And so then another note is that the delay timing accuracy is plus or minus 400 picoseconds. So here I'm going to show some visualizations of jitter that I've done with the oscilloscope. So in order to set up your system, you set up the delay generator as before, but again, still using low voltage pulses. I'm doing impedance matching between the iStar and the oscilloscope, or sometimes I'm changing just so I can show different edges that I would trigger off of. And then because jitter is generally relatively quite small values on the time scale, you want to really zoom in to about less than 20 nanoseconds per division. So in this case, I think I have an impedance mismatching on the left. So when it's triggered off of sort of a less steep area with a bit of noise on it, there's a bit of jitter on this trace itself, but a considerable amount of jitter on the gate pulse, so that you can see multiple different traces moving around there. I'll show in a video in a moment. Whereas if you have 50 ohm impedance matching, this voltage is lowered overall, but it has a nice steep edge right here that is triggered off of, and you can see that the gate pulse comes at approximately, quite almost a similar time every single time, with that very low jitter that it has there. So in the last image here on the right, this is showing a video where you can kind of see that the persistence mode, there's new traces slowly being added onto there. So that concludes the talk today, and in future videos we hope to get onto even more advanced modes of operation of the and/or iStar sCMOS camera. Thank you for watching.